All right, good afternoon, everyone. We'll start out. Can you all hear me? Okay. You can't hear me. Hello? Okay. We're going to start out with any announcements. Does anyone have any announcements for today? Okay, no announcements. So we are fortunate today to have Seth Campbell. He is an associate professor at UMaine and the director of research for the Juneau Icefield Research Station, also known as JERP. JERP is the longest operating polar research and training program in North America. And over the past 2 decades, Seth has conducted glaciology, near-surface geophysics, water and atmospheric research using a range of field geophysical and numerical models and methods. He has broad interest in understanding and quantifying polar change and has participated in over 60 polar field research expeditions across the planet. Seth also spends much of his time developing real learning opportunities for students and other early career professionals, particularly championing marginalized students. So his talk today will share stories and science of polar research and education from Earth and beyond that could impact all of humanity. So thanks for joining us.
All right, thanks for coming, everyone, today. So I grew up about an hour and a half away, give or take, with Christy over here. And someone else in the back here. So I am here to chat with you about the Icefield program, but Carrie asked if I would also kind of share a little bit about my career path as well. So I'll get to that. First things first, I like to do a land acknowledgement. If you aren't sure what a land acknowledgement is, it basically is just recognizing that we are not the first people here. And I'm going to focus on Alaska. Alaska, in the area that I work in primarily, is kind of southeast Alaska, and the indigenous communities in Alaska are the Tlingit or Tlingit. And so I have this acknowledgement on the left-hand side, but I think the important message to take from that is that our Juneau Icefield research program that I work with, we're working really closely with local communities to try to make sure our science and our education is relevant to their communities. So I recommend you all kind of consider that. And there's a website there that you can check out to kind of learn about where different indigenous communities live, exist, their native homelands are across the globe. So it's a pretty neat website to check out. The other thing I want to mention is what I'm going to talk about today is the work of literally hundreds of people. I can't even come close to capturing all those people on a single slide. These people here are faculty and graduate students that I've worked with specifically on the projects that I'll talk about today, but there's still dozens and dozens of other people here that are involved in this work. So I'm going to share, you'll see a bunch of names on the slides as well as I flip through them. So those are the additional people that are kind of involved in this specific work. But recognize a key point for this talk, none of us do this work on our own. You all are standing on someone else's shoulders when you're in your classroom or you're going to be doing a job. It requires a team to kind of do a lot of the work that I'm going to talk about today and a lot of your careers that you're pursuing. So as I said, Carrie asked me to kind of talk about my background a little bit. And so I grew up in Maine. I grew up in a pretty conservative household. I grew up hunting, fishing. We ran a trap line. My dad had a fur buying business, so pretty conservative background. And he was an environmental scientist, so he was focused on doing things like putting radio collars on beaver to kind of figure out their life cycle, their life history, or tracking loons to see how they give birth, how they survive in the Maine climate. And so I kind of got my bug for science early on. And I ended up in college, I ended up working a number of internships through my college time. So the Federal Environmental Protection Agency, Maine Department of Environmental Protection. I did some work for a couple of consulting firms that were environmentally focused. But the moral of the story, I ended up with a lot of education, but this is not because I was good at education. In fact, my undergrad, my high school average, I think, was a C-, and my first semester in college, I think I had a 0.7 GPA for my first semester in college. So not exactly stellar. I think that's like a D- maybe, something like that. I'm now standing in front of you. I did okay. I figured things out. I had a few mentors that really kind of pulled me out of that. And part of my career has evolved from my passions, what I really love to do. And so you see a few pictures of me climbing. This is on El Capitan in Yosemite, and Juneau, which is in northern Maine, and this is in Wyoming. I took that passion and turned it into studying wild places, kind of mountainous environments. So this is Denali, so this is the highest point in North America. So we've done research. I've stood on the top summit doing research at about 20,000 feet above sea level. This is a project on Mount Logan. So this a video is coming out about this project where we drilled an ice core up on Mount Logan, which is the highest point in Canada. So I think the core is at about 17,000 feet above sea level. And I started climbing in high school. I took that skill. I took my background in climbing, and I learned some emergency medicine skills, and I kind of merged that into my passion of finding a job. And it turned out, when I got some earth science skills, I could merge all that together and become a professor somehow. Someone let me become a professor at the University of Maine, and this is what I do. I specialize in a field called geophysics, where we use physics and geology. I combine those two fields of study to understand what's underneath the ground. Right? So in this case, this is in Antarctica, and for reference, for scale, this face right here is about 6,000 feet high, so over a mile high right in front of me. It's hard to tell. That face is probably a mile away from me, it's just so big. What I was doing here is trying to study a glacier system that is significantly changing. It's changing very quickly, and there's some concern about it because it might have the potential for causing global sea level to rise about 1 meter in a very short period of time. So we're studying that. But for me to work in that environment, it took kind of merging all my passions together and building this skill set up. I should also mention that I've worked with Dick Chassé, who some of you may have met at some point in time. So I have a bunch of videos I'll show, some science videos. This is a model, well, it's actually results from a satellite data set that shows ice volume change of Antarctica. And so basically any place that's going red are areas that ice is being lost. So the darker the red or turning black, that area is losing the most mass over the given time period. So from the early 2000s until 2020. This area right here is called Thwaites Glacier. So that was that Mount Murphy, that first mountain that I showed that was about 1 mile high. This is an area that I was working at recently, and I'll show some pictures from there. West Antarctica itself holds about 3 meters of potential sea level rise, 1 to 3 meters, all right? East Antarctica, much, much more. But you'll notice West Antarctica is losing a lot of mass, right? So a lot of us as scientists are focused on studying that area, trying to figure out how it's changed in the past and if it's likely to change more and lose more mass in the future and potentially contribute to that sea level rise. And for reference, all these little dots here are places that I've worked in Antarctica, kind of doing this type of work, trying to understand how Antarctica is changing. So this is kind of a side view of Antarctica, of the Thwaites Glacier area. The color scheme represents velocity, or direction of movement of the ice and how fast the ice. So the red colors, the ice is moving faster. The green colors, the ice is moving really slow, and the little arrows here are the direction of flow, the direction that the ice is moving. So glaciers are basically a big conveyor belt. They form at high elevations, they accumulate from snowfall over and over and over again, and eventually mass causes them to start flowing downhill, and they eventually dump ice out into the ocean. And it's this constant cycle, all right? Now, if you have more mass coming in than ice going out, a glacier gets bigger. So it's kind of like a checking account balance, right? If you put more money in your account and you don't take any out, you're gaining some income, right? Whereas if the ice flows faster than you can put more ice in, the ice is getting smaller. The amount of volume there is getting smaller. So that's kind of what's happening in West Antarctica. So we've studied these sites here, and we're trying to figure out how that ice volume has changed over thousands of years. The idea is if we can understand how the glaciers have changed over thousands of years, we can take that information and compare that to prior climate and try to say something valuable how we expect it might change in the future. So that's kind of what we're doing in this study. So to do that, we bring drilling equipment and we collect rock samples along the exposed bedrock sections. So this exposed bedrock is along Thwaites Glacier, and we collected rock samples, and those rock samples actually have clues for us to tell us how long those rocks have been actually exposed to the air, so not covered by ice. Likewise, we can actually use, this is a drill system, we can drill down through the ice and collect rock samples underneath the ice, and those rocks under the ice also give us clues to whether that rock was exposed to the atmosphere at some recent time. So this is a video of us actually drilling. You see my colleague Grant here basically rotating this dial here, and he's basically pushing the bedrock drill down into the bedrock, and it's going to drill out a core section. This figure down at the bottom, that's an actual rock core that we collected, and we could kind of pull those clues out of the rock to determine if it was in fact exposed. And this is the actual rock in the core. So the question we were trying to answer in this area, has there ever been less ice covering Antarctica in this area over the past 10,000 years? Because we have a pretty good handle on past climate in that past 10,000 years. Again, we know what the climate's like over that 10,000 year period. We can kind of use that information to predict how the ice might change in the future if we compare the climate from those periods of time. All right. So this is Antarctica. Prelude, you get to see some really cool things. This is an ice cave that I lowered myself into and explored. All right. So these crystals, I'm certain nobody's ever seen these. These crystals, this is like a dagger of ice that's probably, I don't know, it was hanging, it's hard to tell there, but probably 20 feet high above me. And these giant crystals, I have a picture in a later slide of these crystals that form underneath the ice over long periods of time, like probably hundreds of years to form these crystals. So pretty rare to get to see some of these places. Point of this slide is love what you do. We were there for science, but I was also enjoying actually seeing these incredible locations, right? We're pretty lucky to see some of the places. You all are going to probably see some pretty incredible places being in your ocean fields in your lifetime. So don't forget to enjoy the time actually being there. All right, so that's Antarctica, and I said I was going to actually focus mostly on North America and mostly on the Juneau Icefield. But I wanted to give you some reference to other places around the globe. And so I showed Antarctica because it's a really important location for Earth's overall climate and Earth as a system. But of course, changes occur in North America as well. So this is, if you don't recognize, we're sitting right here somewhere. And what I'm showing here is a model that shows the retreat of the last ice sheet that covered North America. The Laurentide ice sheet, which is kind of over here, and then they call this ice over here the Cordilleran ice sheet. All right, so this kind of gives you a timeline of when this ice retreated. All right, so everything we're sitting over obviously was covered with ice at some point. At some point in time, where we're standing had about a mile of ice above our head. All right, and we can see that in all the land formations outside. Well, of course, the glaciers have retreated long ago in this area. But there's a lot of glaciers still in North America as well. So Alaska and Canada have a large amount of glaciers. Alaska has roughly 60,000 separately defined glaciers, all right? And the problem we're seeing now is Alaska glaciers and Canadian glaciers are losing a lot of mass really, really fast. So the size of these circles represent how much ice is being lost currently over this time period from 1961 until I think this paper came out in 2019, so about 2018. Right, so you can see Alaska has a really big circle, Arctic Canada has a really big circle relative to these other locations. So Alaska and Canada are really contributing a big chunk of ice to global sea level rise and changing other processes. I'll get to that in a second. Other changes we're seeing in the Arctic. We're seeing changing sea ice. This is going to impact all of you, right? So a lot of you are marine science folks, marine engineering. What are the majors again? So it's Oceanography, biology, yeah. So you all are going to be studying this process, right? My guess is you may have already seen this figure, but this is basically changing sea ice from the late 80s until I think it goes to about 2018. And what you're looking at is multi-year sea ice. So all the bright white is ice that has been around for 3 to 4 years or longer, all right? So it stays over the summer. The areas that are gray are sea ice that wax and wane. They come and go basically every year, right? So every summer they melt, and every winter it freezes up again. And what you'll notice is we're transitioning towards more recent years. there's less and less white, so less and less multi-year sea ice, all right? So that becomes an issue for a number of reasons from an environmental perspective. It becomes a benefit for another number of reasons from an economic perspective, and it becomes a concern for a number of reasons, potentially for some national security issues as well, all right? So there's a lot of complex issues at play here. We're going to stick with the environmental question here. So at this point, you'll see this wide open area that there's a lot of wide open ocean here. There's no sea ice here. Well, what happens when you have a long distance that waves can kind of build up from wind transport? Well, you get coastal erosion. So there's coastal communities, indigenous communities across Alaska and the Arctic that are losing their land very rapidly. So this model was published by a group called the Extreme Ice Survey, and this was a 9-day period. That block was roughly 20 meters wide. So it took 9 days for this coastal block to kind of deteriorate, right? So what's happening is when you have a long, basically waves kind of going from a long distance towards the coast, the sea ice isn't there to kind of slow the waves down, so you have much more active erosion on the shoreline, right? And the take-home point for that is there's 100,000 kilometers of coastline that have what we call permafrost. Has anyone heard of permafrost before? Show of hands. All right, what is it?
It's permanently frozen soil.
Yeah, permanent frozen soil, right? So we have in the Arctic, we have this frozen material, this frozen soil that covers most of the Arctic, right? Well, as we erode and deteriorate the permafrost, we're actually giving off carbon and methane into the atmosphere, and that rate of carbon methane off-gassing is increasing with these types of thaw events. So this is a model of that change, right? So, and I want to exemplify, this is a model. This is not real. This is prediction of what we think could happen in the future. And this came out in 2015. I still show it because it's a good example of what we try to do as scientists. We try to take the most recent information and plug it into our models to predict what we might expect over future decades or centuries. So what we're showing here is any place in red, it's giving off more and more carbon into the atmosphere, all right? That's the prediction from this specific model. So that's the concern. Now, I don't want people to go away from this talk being depressed, because there's a lot of really cool stuff that's being done. This will be the last slide that I show that can be a little bit of a bummer, all right? And it really just talks about what we call Arctic amplification, all right? So this is a NASA visualization from the early 50s, I think 40s, I guess, up until today. And what it's showing is areas in red are gaining temperature, increasing in temperature, and areas in blue are kind of cooling, right? And so what you'll notice is in the Arctic regions, we have a much darker red that occurs. That darker red is what we call Arctic amplification. Those areas in the Arctic are warming up faster than areas in the south. And of course, those areas in the Arctic have more sea ice. They have more glaciers. They have more permafrost. So all those changes basically impact those icy locations, all right? So that's why we as scientists are pretty concerned about that. We want to study that process, and we want to try to make an impact on our overall understanding of the risks of that in the long term for you all, right? And that's what you all are going to be contributing to as well. So now to the kind of inspirational, hopefully fun stuff, right? There's some incredible work that's being done by scientists across the globe to kind of study this phenomenon, these issues that we're concerned with, and work as a team to try to figure out what we can do to deal with this situation. One of those programs is the Juneau Icefield Research Program. The JERP, for short, has been around since 1946, and as Carrie mentioned, it's the longest operating collaborative program of its kind in North America. It's the second longest operating program of its kind in the world. And it was established with the premise that Earth is a complex system. There's a lot of systems interacting with each other, whether it's the atmosphere, these glaciers, the ocean, the ecosystems that surround it, human influences. And the idea was to kind of pick a site that has all those pieces that interact with each other and study it for a long term. And so that's what they did. This was funded originally by military funding, by the Office of Naval Research. The Office of Naval Research was started in 1946, the same year that this program was funded initially. The program itself sits on the Juneau Icefield. The Juneau Icefield, the whole Juneau Icefield is about 4,000 square kilometers in size. And we have 11 field stations spread across the icefield between the US and Canada. It actually straddles the US and Canada. And it sits on one of the deepest glaciers in North America. This glacier here is called the Taku Glacier. And each of these red dots represent field stations. This is an example of one of the field stations. So we bring people there every year through the summer. We bring undergraduate students there every year through the summer. And they learn how to do science in the field with scientists from across the globe. So we have faculty from UMaine, University of Washington, MIT, Caltech, dozens of institutions across the country and globe come to the Icefield. They do real science, and the students participate in that science and learn by doing with scientists from across the globe. They also build this incredible network of colleagues over the long term, whether it's the students that they're working with or the network of scientists that they're learning from and these scientists kind of become their long-term mentors, all right? So I mentioned everything's linked, right? So this whole Earth system concept is a very linked system. And I love showing this figure from my close friend Kristen Tim. She sketched this figure out for a paper published by Shad O'Neill, who now works for the Army, kind of capturing this coupled system in southeast Alaska. So what we see, pretend this is the Juneau Icefield with this ice. That ice is melting, and it comes down into the Gulf of Alaska, and of course that interacts with all the micro ecosystems and the macro scale ecosystem, right? It's all interrelated. How much water comes down off of the glacier region influences everything downstream, right? So it's a pretty simple system to understand. So what we're doing on the Icefield is we're studying a huge number of projects that we have ongoing on a yearly basis. So everything related to climate and terrestrial studies, coastal critical zone research. So that critical zone is kind of all area where life exists, right? Of course, cryosphere, so cryo is cold, so everything frozen, so glaciers and frozen ground. We have a bunch of engineering work that's being done on the Icefield. And again, this is all collaboratively. We have scientists coming from across the globe that work together on this stuff. We even have some planetary research going on, so I'll show some slides about that. Some community experiments, so the idea is someone might have an idea and we come together, we work together to kind of test this experiment. We might test a new sensor or a new system, whether it's a drone platform or a new piece of equipment that's never been tested in the field to see if we can do environmental monitoring in a way that's never been done before. And then of course, a huge amount of field training for our students to participate. So they're getting hands-on experience being in the field. And overall, it's kind of a big Arctic workforce development. There's an estimate that there's about a potential by 50 years, there's a potential for about $70 trillion per year of funding going towards Arctic concerns. That's a huge budget, right? So just for reference right now, the US Department of Defense annual budget's about $300 billion, right? So this is a huge potential future science topic, a huge potential future economy, a huge potential future career for all of you in terms of studying this environment. And it happens to be right out our back door. It happens to be that things that happen in the Arctic have a huge impact on the state of Maine, right? Who's heard that the coast of Maine waters are warming faster than any place else on Earth, right? Does anyone have an idea about why that is? Sure, what do you got back there?
It's because of the Gulf Stream and the Labrador Current.
Yeah, exactly, right? So we're impacted right here. In the state of Maine, our entire economy is based on our environment, right? So it's really important for us to study this process, right? It's really critical for us to study these processes and be ready to change our plans up in the event that it's going to impact us, which we know it will, we know it already is, right? So this is the type of place you can do that. This is the type of place you can kind of build a network to have a lifelong network of colleagues that you work with, right? How are we doing time-wise? I didn't even look.
We're good. You have until 3:50.
Oh, I'm killing it. All right, plenty of time. All right, cool. All right, so this is another example of one of the field sites. This is our biggest camp, so we can house 70 people at a time in this field station. They're pretty rustic. For those of you who have been to like a Maine camp, that's pretty much what you're getting, except it's on an ice field, so it's a pretty scenic spot. This is Taku Glacier, the thickest temperate glacier in the world. This is the thickest part of any glacier in the world, right in front of you. It's about 1,500 meters deep, so about a mile deep, give or take. Pretty phenomenal scenery there. So we have a lecture hall, tons of lodging, a generator shack. We generate our electricity up there, working on updating that to renewable energy. We have a library even. You know, when you fly books up there, we generally don't like to take them down because it costs a lot of money to fly stuff up and down from an ice field. So we keep a maintenance shack. So for those of us that are using the snow machines and generators and science gear, we have a whole building that's dedicated to providing maintenance. We have a 3D printer in there to print parts, for example. So pretty equipped facility. And I said we do a ton of science, right? So I'm going to flip through some slides pretty quickly, kind of rapid fire to give you an example of the science that we do. So number one on my list, I'm technically a geophysicist, but I'm also a glaciologist. So a glaciologist is someone that studies glaciers, right? Pretty simple term. All right, so these are some examples. So Keegan is actually this woman here. She's a graduate student of mine at UMaine now. So I met her on the Icefield in 2018. She decided, hey, I want to do this for a career. She's been a graduate student at University of Maine, and she just accepted a job as a hydrologist, a glacier hydrologist and hydrologist for British Columbia starting this coming spring. All right. She has another job offer to work for a mining company as their resident glaciologist because as glaciers retreat, it's exposing new potential mineral deposits, and so they're working with glaciologists to kind of understand those environments as well. Yui is a PhD student. I am forgetting the other two students' names. Maddie, we've had hundreds of students there, so I can't remember all the students' names, but they're all wonderful. Maddie is a professional climbing guide as well, so she's still pretty active in the community. Kaya Riverman, the bottom left-hand side, is a professor in Portland, Oregon. She specializes in glaciology and geophysics like myself. We're kind of like East Coast, West Coast counterparts, and we work a lot. We work together in Thwaites Glacier that I showed earlier. So she's one of our associate directors for the program. So they're drilling ice cores. Anyone have any idea what we can gather for information from ice cores? How about right here?
Data from isotopes.
Yeah, data. And so what does isotope tell us? Any idea?
Tell you how old the carbon dioxide into the ice levels in them. Kind of tell you how much biomass there was back then.
Okay. So the isotopes are a separate thing from the carbon, but isotopes are huge because we can get annual dating. We can tell how old the ice is. We can also tell changes in temperatures. Like if we have a change in isotopic ratios over a long period of time, that gives us information about temperature. So you're very close. You're very close to getting it. What else can we get out of ice cores? Any other ideas? What about volcanic deposits? Does anyone know the term for a volcanic deposit? Anyone heard tephra? So it's basically those big plume, those ash clouds that get pushed into the atmosphere, right? Those spread out all over the globe, right? And each ash deposit from a volcanic eruption has a specific chemical composition. We can actually trace that chemical composition back to the volcano it erupted at. We can also figure out when that eruption occurred, and that can give us information about climate circulation patterns, right? And how those climate circulation patterns might change. So we can see that in ice cores, right? So we have the chemistry that this fine gentleman mentioned. We have geo information from tephra deposits. So there's a number of things that we can get from ice cores. So we have a number of people that come up to the ice field to kind of study and learn about the ice from ice cores and teach about ice core climatology. Oh, and I mentioned this crystal is actually not a crystal from the Juneau ice field. I threw this in here. This is my hand. You can kind of see it. That's one of the crystals from that Antarctic cave that I showed earlier. So about the size of my hand that I broke off. Kind of neat. I just figured I'd throw it in there because it's a pretty incredible figure. So I mentioned atmospheric trajectory modeling, right? So I mentioned that we can kind of trace how the atmosphere changes with that tephra deposition, right? So what these two students are doing, they have a meteorological station here, and they also collected snow samples, and they were doing isotopic analysis. And what they were doing is they were kind of measuring the isotope signal, and they were back calculating where that original snow deposit likely was evaporated from in the Gulf of Alaska. So what you're seeing here on the right-hand side is a trajectory model of every storm over a given period of time and where those storms are traveling and the elevation above the ground and how they're impacting the Southeast Alaska region, right? So we can use that isotopic signature to actually understand climate processes, right? So this is like meteorology, basically, right? So it's kind of merging meteorology with climate science. Oh, with sound. Great. I guess we do have sound. All right, so here's my friend Allie Balter standing up. Allie's a soon-to-be professor at Tufts University. She did her PhD at Lamont at Columbia University, and what they're doing here is they're sampling rocks. And I already mentioned this technique in Antarctica. Everyone remembers when I talked about collecting rock samples to see when that rock was last covered by snow. If you think about a mountain, on the right-hand side, Yui, who I showed earlier, made this kind of GIF model. We can imagine this mountain is basically losing ice mass. And as the rock gets exposed to what we call cosmic rays, a certain rock type in the rock, quartz, interacts with the cosmic rays and it creates a byproduct, a chemistry byproduct called beryllium-10. And that beryllium-10 builds up at a constant rate. So if we can measure how much beryllium-10 is in the rock, we can tell how long that rock has been exposed. So we can collect a rock sample from the top of the mountain and collect a rock sample from the bottom of the mountain, measure the beryllium-10 in both rocks. The rock sample at the bottom of the mountain theoretically should have less beryllium-10 than the rock at the top of the mountain. So that's what we're doing here, and we can use that to create a deglaciation timeline anywhere we want on the Earth. And that's what we've been doing. So that's what tells us about the past history of ice elevation change over time. I mentioned engineering. So the students here are working with an ice core again. This ice core drill system was built by a professional firm funded by the National Science Foundation to drill ice cores all around the world to do this type of work. They had this new drill system that they wanted to test in the field for drilling. So they came to the Icefield and they worked with our students, and for about a $25,000 price tag for them, which would normally cost about $1.5 million, they got a 300-meter deep core that actually has a climate record because the students were there to help and participate in the actual coring science. So a pretty phenomenal example of what can happen when you have teams working together, right? All we had to cover for cost for them was get the drill to the field and get their team to the field. Our students did everything else. So they have this incredible record as a result of their effort. On the right-hand side, we have a scaled-down Goodyear blimp that we were testing for attaching camera imagery and LiDAR capabilities on the blimp to fly around the ice field. Turns out the blimp doesn't work very well because it's pretty windy on an ice field, so the blimp just kind of wanted to fly down glacier. So we were kind of back to square one, but this was an example of, hey, can we use this technology? It's lighter than air blimp technology. The idea is it doesn't take a lot of power to fly, so we could fly it for a long duration over the ice field to collect a lot of data. I think you can still do it, but we need to modify it to make sure it doesn't get blown away in the high wind environment. So again, an engineering problem. We need science communication in this field, right? Scientists, generally speaking, we like to be cooped up in our offices doing science. Very few of us do a great job with science communication. But this is pretty important nowadays, right? I would argue one of the most important things we could be doing nowadays is understanding how to communicate science. And so we bring science communication experts to the ice field, and we have them working with the students and working with the professional scientists on how we might communicate the science to explain the basics of the science to others, right? For those that don't necessarily have a big science background, right? So this was one student, Grace Juneau, one student's effort to explain what we were seeing from a science perspective. So Llewellyn Glacier is a glacier that flows into Canada, and the science was showing that the glacier itself was losing about 2 meters of ice per day, and this is showing how fast the ice was moving downhill per day. So pretty simple concepts for Grace, so kind of just a beautiful postcard for her. Yeah.
Sorry, it says 2 meters per year.
2 meters per year, yes, not 2 meters per day, thank you. Good correction. And this happens to be next to one of our other camps here that we have on the ice field. Another science communication. So, but tossing out one other field that we have on the ice every year, we have people focusing on ecology and biogeosciences, right? So this is a nice depiction by Abby Case, who was a student, showing what we call the natural vegetation succession of a glacier or previously glaciated environment. So the 1, 2, 3, and 4 represent time periods where we have a glacier that exists in period 1, and that glacier is retreated, and we have what we call primary successors, which are lichens that might attach themselves to rocks. And then over time, those primary successors do a good job breaking up the rocks through mechanical weathering and chemical weathering to develop a soil structure, and that's where your secondary successors, larger vegetation, can kind of overtake the area and start to grow in. This rate varies depending on where you are on the globe. In some areas, it's literally 1,000 years to have that development occur. In Juneau, it's about 100 times faster than it would be for here, actually. It's very, very quick. It's a very quick process in Juneau, which is kind of neat because we can take Juneau and see this process sped up relative to a lot of places around the globe. So a really cool paper just got published by colleagues with the USDA. They have an office in Juneau, literally looking at the soil development. And this was exciting. Our students dug all the soil pits and helped them with the analysis, right? They actually did the real science to kind of come up with this data, right? So again, students are doing real science in real time with the scientists to try to gather an understanding of how this environment's changing. All right, and last but not least, I'm going to go back to my roots, how I got into this field in the first place. I spent about 10 years working in Denali National Park as a scientist, but I got asked to go there because I had a climbing background. That's what got me into this. And I still have that adventure bug. I still love to travel, see these places, and we spend a lot of time teaching students how to travel and live in these environments. So these are 2 students that are learning how to ascend out of a crevasse on a glacier and learning the rope and technical skills to work in these environments. So probably similar to what you might see in a boat, going up a sail mast or any other activities similar to that. So I have a few slides that I'll just flip through just to enjoy the scenery again, because it's worth, remember, taking where you're at. Pretty incredible scenery that we have in this neck of the world. One of the best teaching platforms I've ever been at. All right, so I'm going to transition into the last part of the talk, and the last part of the talk is going to talk about more of the actual science that we're doing on the ice field. So what is the real science that we're doing on the ice field that students are involved in? So I'll start with my field of study. I specialize in a method called ground penetrating radar. It's a geophysical method. Works just like your cell phone does, right? Sends out a radio wave. That radio wave propagates into space. But I just take that radio wave and propagate it down into the ground. And that radio wave travels down through the ground and it reflects off of layers that have different electrical properties. So if we think of a glacier can have snow. It can have multi-year snow, which we call firn, that's getting denser and denser and it eventually turns to ice. You might have ice layers in there. You might have water layers in the glacier. Each of those layers have different electrical properties, so when that energy hits that layer, some of the energy gets reflected back to the surface and is recorded by a receiver. Some of the energy continues down. And if I tow this system along a glacier, I can make a 3-dimensional model of the subsurface. And so we do that all over the world. That's how we know how thick the ice is in Antarctica. That's how we know how thick the ice is in Greenland. That's how we know how much mass exists, how much volume of ice exists in these places. So this is an example from Denali National Park, and I show it because it's one of my favorite profiles I've ever collected because it captures kind of the physics for a very simple case. So this glacier is Kiltna Glacier, and this red line represents this 0 kilometers distance to about 7.5 kilometers distance. So we'll say this is 0 distance, and this is 7.5 kilometers. And this top panel here, there's a lot going on in this figure, but this top panel just shows elevation. So you're basically skiing downhill. So just like if we were at Sugarloaf or Sunday River, You're starting at the top of the mountain, you're skiing downhill. And I'm towing my ground penetrating radar behind me. And I'm basically sending this impulse down into the ice, and it's reflecting off of layers. So I end up with this figure underneath. And so what happens when I go from high elevation down to low elevation, you see all these layers in the ice. Does everyone see that? Right? What about down here? Do we see any layers down here? What happened to my layers? Any guesses? What happens when you go from high elevation to low elevation to the atmosphere? What's that? Yeah. Yeah, so it's warmer down at lower elevation. We have more melt that's occurring. So the snow is melting at lower elevation. That meltwater works its way down in the snow and ice, and it interacts with the radar waves, and it actually destroys the layers that we would use to drill an ice core to look for past climate. So what you're seeing is we would drill an ice core up here where we can see layers. We wouldn't want to drill an ice core down here because all those layers are kind of destroyed, basically. So we often drill ice cores at high elevations or really cold sites because it preserves the chemistry at those high sites. Radar is one of those tools that we can understand that. Now the other thing you can see, this horizon right here, that's bedrock. So this is depth. So I'm able to estimate or measure how deep the ice is using radar as well. Right? So we use radar all over the place on the Juneau Icefield. The challenge with radar, actually I'm going to back up one more. So you'll notice the radar image is really clear at high elevation. So remember, this is up at high elevation right here. But as I get lower in elevation, that signal starts to get washed out. And the reason it's getting washed out, the radio wave is interacting with the water in the ice. Right? So it's kind of killing the signal. Well, turns out the Juneau Icefield is really wet. There's a lot of water. So the video on the left-hand side is from my good friend Aaron Hood. He's a professor at University of Alaska Southeast. It's a time-lapse video. And this is an incredible video of this glacier breathing. What do people think is happening to this glacier? Any guesses? It's water running off the valley walls that's filling underneath the glacier, and the water creates hydrostatic pressure. It lifts the ice up, and then it flushes down into Mendenhall Valley, and it creates these major flooding events in Juneau, in the town of Juneau. If you go online, you can see these flooding events that are publicized annually in Juneau. So that flooding happens right in this basin here. This video on the right-hand side is me traveling through a cave with a bunch of students, just to show you how wet it is in these glaciers. There's a huge amount of water in these glaciers. This cave is actually a flow channel of just a torrent of water that runs through these caves at different times of the year. And the ice is that the cave is retained for a period of time before it closes off. So we're using radar to study the snowpack properties, to study how much water is stored in these glaciers, for example. That's a huge question. We have very little understanding of how much water is actually stored, and I'm saying pure water. Ice is water actually, right? But it's frozen. I'm talking about there's actual water as well stored in the pore spaces and at the bottom of these glaciers, and we don't really have a good handle on how much in Greenland, in Antarctica, in Alaska. So it's a big topic that we're focused on. We do a lot of modeling, and we do a lot of analysis of the data we're collecting to try to upscale. The Juneau Icefield I mentioned earlier is about 4,000 square kilometers. It represents about 15 glaciers, maybe 20 or so. Remember I said there's about 60,000 glaciers in Alaska. We can't possibly get to every glacier in Alaska, right? There would be really, we would need every one of you plus 20 more filled rooms to go to all those glaciers every single year for like the next decade, basically, to get to every one of those glaciers. So what we have to do is we have to upscale to areas that we haven't traveled to. And we do that by understanding what our environment looks like in one local region, and we try to compare that to other regions that are similar. So in this case, we used machine learning. Has everyone heard of machine learning and artificial intelligence? Yeah? Cool. So we used machine learning in this case to take this one radar profile and several other radar profiles to upscale across the whole southern Juneau Icefield, a 700 square kilometer region, to estimate how thick the snowpack was over 1 year. And so that's one of the things that we do when we try to estimate snowfall properties. Why is snow important? Why do we care about snow? I mean, we love it in Maine. We ski, right? I love skiing. Anyone else like skiing? Sweet, awesome. Well, it turns out snow provides water for about a third of the global population. Pretty significant from a humanitarian perspective, right? So this is an important thing for us to understand. How much snow falls every year? It's impossible for us to get to places like the Himalaya and cover all the mountains in the Himalaya, right? Where a huge population in India and Tibet and other regions they rely on this water from snowmelt. So these are the types of things we're trying to do to understand those environments. Other research that I think is just as important. So that was one example of science. We're doing research that's much more focused on helping reach other communities that are more marginalized. Those of us sitting in this room are very fortunate, right? We have resources. We're here, right? There's a large percentage of the population that don't have the resources. So we are now, in the past 3 years, we've had 300 students that are all low-income students and first-generation students in Alaska the past 3 years to participate in all the science that we're doing, to give them kind of a leg up, fully funded for them to go to Alaska and work with us. We're starting that program here in Maine this coming year. If you're interested in that, I'm not going to spend a lot of time on that here. Come see me if you want to get involved in something like that, because we're looking for students that would be keen to help develop that program and expand it to reach more kids. I mentioned this project already. Based on time, I'm going to bounce forward pretty quickly. There's a few more cool slides that I'll show. This is an example of an engineering project. This is a seismometer and a GPS system that is designed to basically kick out the back of a plane 5,000 feet in the air, land on a glacier, and start recording seismic activity and start removing ice movement, with the idea that it's way cheaper to just boot something like this out the back of a plane than it is to land on the ground, dig a hole, put a seismic system in, which takes multiple days to do that. Way easier just to boot it out the back of the plane, all right? Turns out this guy, Jeff Hoffman, is from MIT. He's also spent 50 days in space. So he's one of our faculty members, kind of a cool faculty member to have on the team who kind of brainstormed this idea. And again, Keegan, the grad student. All right, so I said I'd show a couple slides for planetary purposes. When I was growing up, this movie, Armageddon, was pretty big. Has anyone seen the movie? Okay, cool. All right, so I think I was out of high school at the time that it came out, but of course most of us thought this was kind of crazy. If you haven't seen the premise, it's an asteroid coming to Earth. They have to go drill on the asteroid and blow it up, all right, to make sure it doesn't hit Earth and we're not catastrophically wiped out. More recently, The Martian, right? So that's a classic book, good movie as well. Well, recently I was asked to help a team with NASA to do their first crewed mission to Mars, and the reason is their planned mission is to drill ice cores on Mars. Kind of made me laugh a little bit because we thought this was maybe crazy stuff to think about this. But we had a team of scientists from across the planet talking with NASA and trying to brainstorm how we might do this, how we might pull this science project off. And what came of it is we should be testing ideas on places like the Juneau Icefield. And in fact, that's exactly what happened. We now have a project that we're testing a system on the Juneau Icefield, not for Mars, but for a different location. So these are examples of what you might see on Mars. So this is kind of the central region of Mars where you break off a little, get a little of dirt out of the way, and you have this icy area. Right? We are working with NASA Jet Propulsion Laboratory to try to build a drill and send it to Jupiter's moon Europa to drill through the icy shell of Europa to look for signs of life. Wouldn't it be cool if we found signs of life on a different planet? Right? So the drill has to be autonomous. It has to be able to drill itself through the ice and analyze the water sample to see if the water sample has any evidence of life. So that's the type of stuff that we're working on. And this is one of the sites that we're drilling. So this coming summer, we're going to be drilling into this area. You can see these concentric cracks right here. A subglacial lake forms in this basin right here. So this is kind of a bird's schematic view. You have a liquid reservoir that forms underneath this, and the cracks are a result of the ice getting lifted up and then dropping down and lifted up and dropping down as that water fills the cavity and then drains out to the glacier. So we're going to punch a hole into this area here, and we've used radar to map ice thicknesses to find the deepest area to figure out where the water likely pools. So this is the deepest area. This blue area is kind of right in the middle here. So that's where we're going to punch a hole. And I think we're done.
1 minute left.
Oh, that's good. So that's the science that we're doing on the ice field. Take-home points. everything we're doing as scientists is pretty complex, right? So trying to work together with people from different fields is pretty critical moving forward. So make friends with scientists that are not doing science in your field. We have lots of opportunities, so come see me if you're interested in any of the opportunities we have. Come see me if you're interested in JERP. And then my final career advice, back to Carrie's original question for me, was every piece of experience you get in the classroom, in your field, in internships is valuable to you. Use that and try to merge those opportunities into your career. That's going to serve you well as you move forward. I think with that, I'll call it good. Thanks.
I think we have time for one question. And I saw it.
Yeah.
So climate change plays a significant role in the Arctic and Antarctic.
Yep.
What aspect do you think is the most worrying about climate change, whether it's methane emissions and permafrost or increased fetch causing erosion?
I think it's honestly science literacy. It's not, we know really what we need to know from a science perspective. We've solved major problems before. You know, think about the ozone problem. I think I would challenge you to look at our representatives, how many people are representing us that actually have a very strong science background. I think that's one of the challenges that we face. And that's not, it's just that we don't, it's not a requirement for so many students, right, that are being educated. I'll use the example. I bring my vehicle to a mechanic. They fix it. They know way more about the maintenance of my car than I do, right? You might have a doctor perform a surgery. Trying to make sure we trust our scientists that are focused on this type of work, I think, is the biggest weakness we have. From a science perspective, I think Antarctica is the concern of Western Antarctica is a legitimate concern from the potential for a meter sea level rise, because we can't change coastal cities that fast, right? And the risk is a meter sea level rise in the next 50 years, changing where a large percentage of our population lives that fast is going to be a really challenging thing to do. So I think that one right there is from a science perspective.
Well, thank you so much for joining us.
Sure.
One more round of applause.
Thanks all. Cool. A little long.